In this module, we will make you aware of some incredibly advanced radio and network technologies, as well as the important companies that have created these innovations within the wireless ecosystem. We will also try to predict how these technologies will continue to evolve in the near future. The first few technologies are focused on the access layer of the wireless system. Let's start with cellular technology. This idea applies to both cellular base stations and Wi-Fi access points, but we will discuss it in the context of cellular base stations. To provide wireless access over a certain area, the cellular concept deploys a network of base stations, each covering a certain smaller area called a cell. As a mobile device moves from one cell to the next, the connection undergoes handoff between the base stations. Interference among cells can be managed by assigning specific frequency channels to the cells, for example, the classic 1/7 pattern of frequency reuse illustrated here. Note that cells spaced far enough apart can use the same frequency channels because they do not interfere with each other, an important technique referred to broadly as spatial reuse. As a final comment, I am sure you can imagine that making this system work requires significant coordination and synchronization among the base stations, often involving additional core network infrastructure to connect and manage them. So that's cellular technology. Another important technology is radio devices on either end of a link having multiple antennas. The idea is to design radio devices with an antenna array along with associated circuitry and signal processing. Such an antenna array can be used at a transmitter and/or a receiver to steer electromagnetic energy into particular directions, a technique called beamforming. Antenna arrays at both the transmitter and receiver can be used to send parallel streams of data simultaneously, a technique called spatial multiplexing. Because of multiple transmit and receive signals, such approaches are often referred to as multiple input, multiple output, or MIMO technology. Recent generations of Wi-Fi, like IEEE 802.11n and AC, and cellular standards, like 3G and 4G LTE, include such antenna array and MIMO technology, at least in the base stations and access points. So that's multiple antenna or MIMO technology. Network densification represents another important technology direction. We'll highlight two densification technologies, sectorization and small cells. Putting the cellular concept and multiple antenna base stations together, we can break cells into smaller areas called sectors. Sectorization allows both higher data rates and increased frequency reuse, and has been an important ingredient in 3G and 4G cellular. As you can imagine, a multi-sector base station driving multiple antennas for each sector gets to be a large, expensive proposition. Such a base station is commonly called a macro cell base station for reasons that will become clear shortly. An alternative and emerging approach to densification is small cell or heterogeneous network technology. Here, the idea is to use smaller, lower-cost base stations with higher density than traditional macro base stations. Small cells are intended to provide higher capacity in targeted areas to augment the coverage of the macro base station. It is also worth noting that small cell base stations are starting to look more and more like Wi-Fi access points. So that's network densification technology. The next few technologies are really focused on the physical layer of the wireless system. A major advance here is orthogonal frequency division multiplexing, or OFDM. The idea is to break a band of frequencies into multiple subbands, create a separate signal for each subband, and then add them together. In the frequency domain, the signals look the same as if we had a narrowband digital radio for each subband. However, we have a very efficient way to implement OFDM using digital signal processing, or DSP, in a single radio. OFDM makes it easier for systems to deal with propagation effects that vary across frequency, because each subband is narrow enough for the channel to look flat over it. Specifically, OFDM can adapt the power and data rate allocated to each subband to improve overall system throughput, reliability, and so forth. OFDM actually started in digital subscriber line, or DSL, transitioned to Wi-Fi in IEEE 802.11a and G, and most recently transitioned into cellular in 4G LTE. So that's OFDM technology. Software-defined radio, or SDR, and Cloud Radio Access Networks, CRAN, are two additional but related technology developments. The idea is that significant radio functionality is implemented in software on programmable processors rather than in fixed analog and digital circuits. This allows more adaptation and reprogramming even after the system has been deployed. SDR became popular in the context of military systems, and it has gradually been making its way into the commercial sector, mainly in base stations. Flexibility generally comes at the price of increased power consumption, keeping SDR from being a viable option for mobile devices and consumer electronics like Wi-Fi. C-RAN can be viewed as the next step in the evolution of cellular SDRs. Instead of a base station being a single box with programmable processing and radio electronics, we separate the base station into two parts, a remote radio head that encapsulates the radio electronics, and a processing node that encapsulates the programmable signal processing. The processing node can ideally be a commodity rack-mounted server machine that we put into the cloud, which has tremendous advantages in terms of cost and maintainability. So that's SDR and C-RAN technology. An emerging technology area is millimeter wave systems for mobile wireless access. The idea is to utilize frequencies above 10 gigahertz that are relatively open, at least so far. The much higher frequencies and significantly wider bandwidths available through millimeter wave present challenges in terms of circuit designs for consumer devices, transmission signaling, and network architecture. There is an existing Wi-Fi standard, IEEE 802.11ad, based upon millimeter wave at 60 gigahertz, and there are several cellular prototypes being developed by companies like Samsung, Nokia, and Huawei ahead of potential cellular standardization efforts for 5G. So that's millimeter wave technology. Another emerging technology area is spectrum sharing, which presents numerous technical, economic, and regulatory challenges. The idea is to allow radios to dynamically identify and access spectrum that has been assigned but not fully utilized, either at some locations or sometimes or both. In this context, the primary system has priority access to the frequencies because of an assignment, but the secondary system can access the spectrum provided it does not cause harmful interference to the primary. There are three key mechanisms being considered for allowing the secondary users to identify accessible spectrum: geolocation databases, spectrum sensing, and primary beacons. And different systems can combine one or more of these. The original motivation for spectrum sharing arose in the context of underutilized broadcast television channels, and two standards have emerged: IEEE 802.22 and IEEE 802.11af. However, in the US, the approach to this problem has shifted to being addressed by the television ban incentive auctions, which may limit the impact of these technical standards. With the continuing growth in demand for spectrum from both commercial and government systems, numerous reports from governments around the world, such as the PCAST report and NTIA 1755 MHz report in the US, are calling for innovative spectrum sharing and dynamic spectrum access among these systems. So that's spectrum sharing technology and policy. All of these technology developments are very impressive, but the organization of the industry behind them has become very sophisticated and interesting in its own right. We have divided the industry into four segments shown here. There are chipset and component companies like Qualcomm and Broadcom. Equipment vendors like Alcatel-Lucent, Cisco, and Nokia make the base stations or access points and network infrastructure to enable wireless access. Mobile device manufacturers like Apple, Samsung, and Nokia design and sell handsets, tablets, and other connected things that incorporate radio functionality. Operators or carriers like AT&T, Verizon, Sprint, and T-Mobile in the US acquire spectrum licenses, deploy networks, and charge mobile users for voice and data service. As we wrap up this module, let's take an opportunity to predict how all of these technologies might continue to evolve in the near term. Based upon recent trends, I believe we will see more of the following: convergence of cellular and Wi-Fi, blurring the lines of licensed and unlicensed frequency bands, more spectrum sharing and dynamic spectrum access, and utilizing much higher frequencies above 6 gigahertz. Large and small cells, multiple antenna systems, OFDM, millimeter wave, software-defined radio, and spectrum sharing are all exciting technologies developing within the wireless ecosystem. We have just given a high-level overview of these technologies, with the hope of sharing a sense of the tremendous innovation engine running behind the scenes to support use of your mobile device and all of its killer apps. Perhaps you're interested in learning more details about some of these technologies, or even becoming an innovator yourself, in which case we encourage you to dig deeper in technical articles, patents, and product information. Some pointers are available on the course website.